Okay, in this exercise, we will speak English because we have to introduce a lot of new terminology, and therefore it is better to do it in English. So the title of the exercise is Conditional Statistics Revisited, and basically we want to look back at one exercise that we did during the workshop in the theory course of statistics when we were discussing the conditional probability in the theory of probability, and then we will look at this exercise from a new point of view, namely the point of view of the method of the confusion matrix. Okay, so the exercise starts with the basically the first question, which is just to draw the tree diagram. There is some information is given about some diagnostic test. We can detect a viral infection, and the information it is given here. So basically, you already did this. We have to fill in the probabilities. So if we read what the information is, we see that for example, it is say that here that 0.005% of the population has been infected. Okay, that means that we can put here by infected, not infected. So this is the probability to be infected is 0 equal to 0.005 because it's the 0.05%. Okay, this means automatically that the probability to be not infected, it is equal to 1 minus this pi probability. Okay, so we use this basically information. Then it is also say that in the case of a patient which is infected, the test recognizes the virus in 98%. So this is the probability to be tested positive in the case that you are infected. So here we can put equal to 0.98. Okay, and this means that the probability to be not infected to result negative at the test, and given that you are infected, that must be equal to 1 minus this probability. Okay, finally, it is also given that in the case that the patient which is not infected, the test gives a wrong positive result with 0.2. Okay, this is the probability to result positive at the test given that you are not infected. And so this is 0.2, so this is equal to 0.002. And then we know that this other probability must be equal to 1 minus p given not infected. Okay, in order to complete the tree diagram, then basically we have to find these probabilities, namely here, for example, the probability that you are positive and infected, and for that we can use the base formula, basically so probability that you are positive and infected is given by the product of the probability that you are infected times the probability, the condition probability to be tested positive given that you are infected. This means that we have just to take the product here of this this probability times this other one. Okay, and the same is true also for the three other probabilities, just by means of base rule. Then we get here this is equal to IE times this other probability. Then we have here pi NI times this one, and the last one also with Bayes formula. Okay, this means that at this point the tree diagram is complete, and then we can move, I take the result over in my slides, and we can move to the next question, which is calculate the probability that if the test is positive, the person is actually infected. And okay, this is the typical examination question or workshop question. So basically what is asked here, it is, we see that, so the probability, oops, it says the probability that you are infected, oops, given that the test gives a positive result, and we see that it's just the other way around of this probability. So this probability is not displayed in our tree diagram. So, you know, we can calculate this by means of Bayes formula, because then you get this equal to the probability to be positive and infected divided the probability to be positive. Okay, and the probability to be positive and infected, we have it here. So this is in the numerator, and then in the denominator we have to consider the total probability to be positive. Basically, is the sum of these two probabilities. Okay, so basically this, it will be, I can fill some result, say here, this will be equal to this probability divided, and then this probability plus the probability to be positive and not infected. Okay, and then basically if you round off this with 3 decimals number, basically we get 0.197, so about 20% probability. Okay, so this completes the answer to the second question, and in the next question you are asked to draw the corresponding confusion matrix. Okay, for that we should first give a brief introduction to the method of the confusion matrix. Basically, a confusion matrix describes the predicted number of successes compared with the number of successes actually observed, and similarly compares with the predicted number of failures with the number actually observed. What does it mean? It means that first we have to define what is what has to be considered as a success. In, for example, in our case of the diagnostic test, and in the case of the diagnostic test, we consider a success as the detection of that somebody has been infected. Okay, and or we consider failure basically when somebody is not infected, when somebody has no condition, when the condition is not detected. And you see that in this case we are dealing with the case of a diagnostic test, but the same basically apply if you would consider, for example, in law, the case that somebody is guilty, or also in the case that somebody is pregnant, in the case of the test is about to be pregnant, or more important for us, for the students for who is going to make engineering next year, in the case of MRO, then we consider success, say, the detection of some mechanical or electrical issue or breakdown. This is quite a bit annoying, the fact that we consider actually a success in MRO the detection of a failure. Okay, so the choice of the word success and failure is not the best one as far as MRO is concerned, but unfortunately, that's what is used everywhere in literature. Okay, so you have to deal with it. And okay, so always to consider that somehow in our case, okay, in this specific case, the detection of success means that detection that somebody has been infected. Once you make this assumption, then you see that you can somehow put all these probabilities into a matrix form, let's say, which is called a confusion matrix, where you have so the different cases, namely positive and infected. So these are the true positive. Okay, of negative and infected, these are the false negative, or positive and not infected, these are the false positives, and negative and not infected, true negatives. You see that I also use some color code in this matrix form, where you see that on the basically on the x-axis I have basically what is true, the true condition, namely to be infected or not infected. In this case, success is to be infected and failure to be not infected. And on the y-axis I have the prediction. So success prediction means prediction to be infected, and failure prediction to be not infected. Okay, and then you see that you can sum up along at least 4 different directions. So for example, if you sum along this direction, you get somehow all the predicted positive. So these are the total probability to be here predicting negative, and this is basically the sum of the true negative and probability for false negative. Then here you have the total probability for being predicted positive, and along the y-axis you see you have the observed negative. So it means the total probability to be in reality negative, and here the total probability observed positive, namely the total probability to be positive. Okay, we need this partial summation terms because we will use this in the definition of some measures that we will introduce later on in order to better describe basically this case of the diagnostic test. So the reason for this confusion matrix is because this gives access to what is happening, somehow to give access to much more information than what you will get just simply by this tree diagram, as we will see. Okay, so now that we have established a relation between, also with colors, as you can see, between the tree diagram and the confusion matrix, it will be easy to basically to draw this matrix, and that's what we are going to do. And so I just need to fill in these cells here. So here I will put this probability, then here I will put the gray probability. Oops. No, some problem here. Okay, in the green one, the false negative probability, and here by the true positive, the light red probability. By the way, we are working here with probabilities. I could also work with the number of cases. You know, if I multiply the probability times some fixed number, which is just a sample, I could, for example, take a sample size of 1 million people. Then I will work not with probabilities, but with the numbers. But basically, will be the same. Okay, you have always to normalize basically all these numbers to the total amount of, in this case, person in the sample. So in order to complete the matrix, we have also to sum up, as we had said, for example, to find out all the total observed negative. Okay, then here the total observed positive, let's say infected observed. So this plus this, and we have to check that these two together must be equal to 1, because everybody is either infected in reality or not infected. So the total probability must be 1, and actually it is. And the same way we can sum up along the horizontal axis. So for example, all to calculate all the predicted negative probability. So this is equal to the sum of these two probabilities together with the total predicted positive probability. Okay, and we have to check also that these two together, they must be equal to 1, and it check actually it is. Okay, so in this way we have drawn the confusion matrix for this diagnostic test example. Okay, then I take the result over here in my slides, and I go to the next question. Basically, this is we have to calculate the following measures, and here I have at least 6 definitions, which I have to first explain and then to calculate. So the first measure that we should calculate is the true positive rate, or also called sensitivity. And we see that according to the definition, this is given by the ratio between the true positive, so I write here the definition, true positive, divided the total observed positive. So basically, you see I have to sum here along this column here. So I have here divided false negative plus true positive. Okay, and so this means that for the sensitivity we have to take the true positive and to divide it by the true positive plus the false negative. And you see I get here a value of 98%. Okay, so what is this sensitivity? You see there is the definition here. Basically it is, and that's the reason why it is also called the power, basically the probability of detection. And basically it tells me how good the test is in spotting somebody which is actually infected. Okay, then the second quantity is the specificity, or also called the true negative rate. Okay, for the true negative rate, from according to the definition, I have to take, you see, the ratio between the true negatives here, true negatives divided, and then you see I sum here also along this column where I have the observed not infected. So the true negative plus the false positives. And if I consider the number in our case, then I get this probability divided the same probability plus this other, and also I get a very high probability of 99.8%. Okay, and what is the specificity? Then if I look at the definition, this true negative rate, basically tells me how good the test is in spotting somebody which is not infected. Then the next measure that we are going to consider is the accuracy. And so we see that the accuracy is given by the ratio of the correct predictions against the total number of cases. So this means that here this is just the sum of the true negative probability plus the true positive probability, and if we are going to calculate, so we have to sum up true negative plus true positive, and then we get also very high percentage of almost 1, because if I round off this, okay, 0.9998. And notice that in this case I have basically no denominator, because the total probability must be 1. Then what we have is the false positive rate. Always okay, and the false positive rate basically I don't have it here in my scheme, because you see this is just is the ratio of the false positive divided the total observed not infected. Okay, so it is just 1 minus this specificity. Okay, so it is, if the specificity was 0.998, this would be 0.002. But okay, this is important because you see that somehow this is false positive rate, so the amount of false positive about among all people which has not been infected basically is the probability of false alarm, also called fallout. Okay, and basically we will see in to exercise this when we look at the probable binary classification. It will turn out that this quantities, this measure, the false positive rate, together with the true positive rate, so the sensitivity, they will be the most important one. Okay, then we move to the next one, and you see up to now we have summed always, okay, with the exception of the accuracy, by true positive rate, true negative rate, false positive rate. We have always summed along the vertical direction, the columns, and in the next one we are going to sum across horizontally along the x-axis. Now, by the way, you can imagine that we are there will be more combination. We are looking here at 6 combination possible, but there are in principle more combination where I can take this rate along the columns or the rows or a different way, like the accuracy. But okay, I made some choice to discuss only these 6 because these are at first instance the most important. Okay, but depending on what is the specific problem, then you have other measures, because you have other combination where you can somehow measure the rates in this classification table. So the next one is the positive predicted value. I need a color. Okay, and this is also called the precision. So if we look at the definition, we see this is the ratio of the true positives. So true positive divided basically the total predicted negative. The total predicted positive. So I have to divide by the true positive plus the false positive. So here I have true positive plus false positive. Okay, and if I try to calculate it with the probabilities, then I have a true positive, so this number divided, and then I have to take it again, plus, and I have to look along the horizontal axis. I get a false positive divided, and then I see here that okay, I get a lot of decimals, but what is really interesting is that you see that I get basically a very small, let's say much smaller probability than, for example, what I have in the specificity or the sensitivity, so only 20%. So then you will think that this test actually is bad because it has very low precision. But okay, we will put some general comment in at the end of this exercise. As you will see, I mean, depending on what is the meaning of the test, then we have to select which one of these measures is the most important. At the moment, we just registered that this precision is relatively small, and this sounds definitely bad. Then the last one is the negative predicted value, and so it is basically the same, but now we have to take the ratio of the true negatives we see in the definition against the total predicted negative. Okay, so we have here true negative divided, and then I have true negative plus false negative. And if I look here at the numbers, then what I get is so the true negative divided, and then true negative plus the false negative, and here I get actually a value which is extremely high. So if I round this off, I get, I think, basically 1. Okay, so now the question is, let's go back to comment this result about the very small probability for the precision. So does it really means that this diagnostic test is very bad? I think this problem is very actual, because this could be basically the classification table for the PCR test in the case of COVID-19, for example. And then you see that basically, what does it mean, low precision? A low precision, it means that probably I have a large amount, relatively large amount of false positives among the people which has been predicted positive. And okay, of course, this is bad for somebody which has been gets the result of the test is positive, but it's actually not infected. But you see, it has no consequences for the society. Basically, this person should just stay home, and okay, nobody gets problems because of that. While if we look at the sensitivity, you see that in the case of, for example, PCR test for the COVID infection, the fact that this is very high, this is very important, because if the sensitivity is very high, then you see we have very few false negatives, and this basically means that you will prevent people which is infected to go around freely and to be free to infect other people. So you see that the sensitivity is much more important than the precision. Okay, and so that's why I think is also in reality, okay, these numbers are taken from some exercise, but as far as also the tests of the COVID infection are concerned, I think that in that case also, if I remember correctly, we have that the sensitivity for the molecular test is also about 98%, and the sensitivity of the quick test, I think the antigenic test, is lower, somehow about 0.8. Okay, but definitely that in that case, the sensitivity, the probability of detection, is the most important measure for a diagnostic test in the case of a viral infection, which can generate a pandemic disease. So you see, that's why also I remember at the beginning of the year 2020, there were people that were claiming that somehow that test was basically not important because it has a very low precision. Okay, you see that this can be true. Okay, but actually, if you look at the technical definition of the precision of a diagnostic test, then we see that the fact that the precision as a measure is low, this has no consequences, while the sensitivity is the most important measure parameter that we have to consider. Okay, so we have answered question 4, and then in the last part of this exercise we will answer a series of questions where you don't need to calculate, but where we reflect about this basically these measures that we have introduced. So the first one is question 5, and in this question 5 where you have to tell which of the following statements is correct, then you will probably, I always advise you to stop the video, try first to answer this question by yourself, and then to look at what the solution is. So if you think about, in this case, because what we have said about the sensitivity and specificity, it is obvious that here the correct question answer statement is statement B, because the sensitivity is a measure how well a test can identify true positives, and specificity is a measure how well a test can identify true negatives. So we already say that the sensitivity is how good is the test in identifying people which is actually infected, and the specificity is how good the test is in identifying people which is not infected. Okay, then we move to question 6. And in question 6 you have to complete the following sentences, and I think if you think about, then you agree that the correct answer here is just to fill in is false negatives here, and it will require a very high sensitivity. Okay, it is because you see that basically in the formula here for the true positive rate for the sensitivity is very high when the false negative is small in comparison with the true positives. Okay, so you have, if you want to have very high sensitivity, and you have to have a small number of false negatives, and so you will avoid in that case that when you want to identify everyone which has an infection, because you want to avoid the side effects, which is what we mentioned just before, that for example people which is infected can go freely outside and infect other people. Analogously, we see in the next question, basically if the goal of the test is to identify people who do not have the infection, if you remember what we said about the specificity, then it means that you should minimize, let's say, the number of false positives in order to have a very high specificity, because we see that in the formula for the specificity is very high when the number of false positive is small. Okay, and that's important when somehow you want to avoid false positive, because maybe, you know, if you get a positive test, then people either get, of course, worried about their condition, or that's not the case in the case of COVID. It could be that this would mean some extra further test with some extra expenses and economic financial basically load, which is unwanted. Okay, so we have completed question 6, and we move to question 7. And in question 7 we explore more the ideas about sensitivity and specificity by means of this question statement that we have to complete. So we have seen that high sensitivity means that the test is very good in spotting somebody which has been infected. But what about if you get a negative result? does a negative test means if you get a negative result for the test means that you can feel safe, and so is useful for ruling out the disease or just for ruling in the disease. Now, if we look at the formula for the sensitivity, an high sensitivity means that the false negative are relatively small. So there is a very small probability to be a false negative. So if you get a negative result, I would say that if the test has a high sensitivity, then its test will be useful for ruling out the disease. And this is actually indeed the good answer. In particular, you see, if I will have a test which has 100% sensitivity, so this means there are no false negatives, then that basically will definitely rule out the presence of the disease. And what about then a positive result in a test with high sensitivity? Is the fact that sensitivity is very high means that somehow this is useful for ruling in the disease, or not necessarily? That this means that then if the sensitivity of the test is very high and I get a positive test, does it mean that I'm 100% sure that I'm infected? And here the answer is not necessarily useful, because how can we see this? Okay, so suppose for example that we have a quick test which is designed to always give a positive result. Okay, so this will be a test with 100% sensitivity because it tells everybody which is positive. Okay, but on the other end, it doesn't take account false positive. So it means that this quick test basically it will be definitely not useful, or basically will be useless for detecting or ruling in the disease. And that's what we see here also, that in the definition of the sensitivities, basically the false positive does not enter in the formula. So basically the sensitivity does not say anything about a false positive. And so it means that if you get a positive result also in a test with high sensitivity, it could just be that you are false positive. So it is not necessarily useful for ruling in the disease. The third question, the third and the fourth, they are about the specificity. So we see a positive result in a test with high specificity is useful for ruling in out the disease. So here the question is, I have a test with a very high specificity and I get a positive result. Now, if we look at the formula for very high specificity, this means that basically I will have, if the specificity is 100%, then I have no false positives. And that means that basically if I get a positive result, then in this case it means that I am infected. So you see, this means that then that a test with high specificity is useful in ruling in the disease when I get a positive result. Okay, and what about the last possibility, if I have a test with high specificity and I get a negative result? Is this useful or not necessarily useful? Basically, it is like second case by the sensitivity is not necessarily useful, because here we can also consider the case with a test which always return a negative test. So this will have 100% specificity, but does not consider false negatives, because we see that in the definition of the specificity we have no false negative. They don't play any role. Okay, so basically it means that a negative result in a test with high specificity, because high specificity does not consider false negatives, is not useful for ruling out the disease, because I can still be infected. Okay, and what I want to stress, as you see, in all these answers here, basically I made use of the definitions, basically of the formulas here, which define these parameters. And that basically the best way in order to try to think about this specificity and sensitivity and the other measures. And moreover, you see also that it helps a lot to consider, once you have in your mind this confusion matrix, to consider this kind of summation, partial summation along the y-axis or the x-axis. And that's why, of course, it makes for us more sense to talk about sensitivity than to talk about true positive rate, and to talk about specificity instead of true negative rates. But the moment that you use these definitions, then you see that you can immediately recover from what you have in your mind about the confusion matrix, what are the definition of these measures, okay? Because you just take the rate of these cells along the y direction in the case of sensitivity, specificity, and along the x direction in the case of the precision and the reliability. Okay, so at some point the expert in this field always thinks in terms of these definitions: true positive rate, true negative rate, because it immediately you know immediately what you have to do with the confusion matrix. Okay, this is some kind of hint that I can give you in order to better remember this method. Then in question 8 we are asked to look back at our tree diagram, and basically if we look carefully, then we see that at least the two measures that we have introduced that we already had in the tree diagram, only at that time we were calling them in a different way. And basically you recognize here, this is the probability that to get a positive test result given that you are infected, and here you have the probability to get a negative test result given that you are not infected. You will probably recognize here the definition of specificity and sensitivity, because we see that this probability, it is just 0.98, and this also was 998, and this follows also from the definition of the formula of Bayes, because basically for the probability to be predicted positive given that you are infected, it is given by the probability to be positive and infected divided the total probability to be infected, okay, which is indeed, this is just true positive divided false negative plus true positives, okay, which is the total observed positive probability. Okay, so you see that is basically exactly the same, only derived in two different ways. And the same is true for the specificity, so P to be negative given that you are not infected is equal to the probability negative and not infected divided the probability to be not infected, and this is just, you see, is what we have here. Probability to be negative, not infected, are the true negatives, probability divided the total probability observed negative, so true negative plus false positive. This total probability here. Okay, this is just to remember you that we have not, I mean, the information was already stored in the tree diagram, but you see the classification matrix gives a more systematic way to assess the information of the, in this case, diagnostic test. Eventually, in the last question 9, we ask you to set the analogy of this problem with the classification metric about a diagnostic test, to set the analogy with the field of MRO. And we have said at the beginning that the analogous, which have to be considered success, as in the case of the detection of the infection, in the case of MRO, it will be the detection of some mechanical or electrical malfunction or failure. And this means that the theory that I have developed now for the case of diagnostic test can be fully developed analogously for the case of MRO, just by changing the definition of the words. Like, for example, in this case we had the diagnostic test. In what is a diagnostic test, PCR test for COVID, for example, in the case of MRO, we call it inspection. So the condition of being infected we have identified as success. It will be basically a mechanical or electrical issue of malfunction. The condition of not being infected, it would be basically no malfunction, there's no issue. And then positive test result, it would be in that case some kind of alarm, some red light which turns on. And the analogous of false positive test result and false negative, it will be basically in the first case alarm but no malfunction, so kind of false alarm, and in the second case just an unseen malfunction, which we know in aviation is definitely better to avoid. Okay, this complete the exercise which we thought it can give you some kind of bridge between what you have seen in the naive theory of probability when you were studying conditional probability, and the method of classification, the classification method, which is a method which is used in descriptive statistics, so to approach more systematically the problem of the binary classification. Okay, so in the next video you will ask to fill again confusion matrix, but we will move from the this naive problem of the classification matrix method to the more general problem of the binary statistical classification, and we will introduce another method which is also used in descriptive statistics together with the classification metrics. Okay,